for the hydration, using small rates or limited rates for lignin and waste vegetable oil. So we can see that with the lignin, we can see a delay in the hydration process. And this delay is due to a chemical reaction between lignin and calcium that we can find in clinker, in the phases of clinker. On the other hand, using the waste vegetable oil didn't show any delay, but we can see just a decrease in the intensity of the peak. It's due to limiting the contact between water and cement, due to introducing more air and this hydrophobic nature of oil. So we can see that we have maybe the same effect regarding the intensity of the peak, which is both of them reduce the intensity of the peak, but the reason behind is different. For lignin, it's a chemical reason, which is the complexation between lignin and calcium. But for the oil, it's different. It's a physical reason, which is this hydrophobic and introducing air inside the cement paste. So this slide presents the effect of lignin and oil on the compressive strength of cement paste. So we can see for low rates of lignin, the effect is limited, and we can say that it's the same. It's the same compressive strength as the control one. We can see a decrease with 1%, but the values remain acceptable. However, for the oil, we can see a high decrease when we increase the rates introduced in the cement paste. However, comparing lignin and waste vegetable oil directly can be misleading by saying just these two figures, but we need to compare the same percentage. For example, if we take the same percentage for lignin and for oil, which is the 1%, we can see that oil gives more or show more or higher strength than lignin. So they both reduce the strength, but it's still acceptable at a certain rate, which is 1%, for example. And also, as we said before, the impact or the reason behind this decrease is not the same for lignin and oil. For lignin, it's a chemical effect, which is this delay of hydration, which is this complexation with the cement phases. But for the oil, it's different. It's a physical effect, which is introducing more air in cement paste and increasing the porosity of the cement paste, and then decreasing the compressive strength of cement paste. So here we want to combine the two additives in the same cement paste. So we want to study the interaction between oil and the lignin in order to see if there are something new to see. Maybe if we put them together, that could increase or improve the quality of the cement paste, or maybe decreases more the quality. So here we can say that for example, the effect on the hydration, it's just the sum of their individual impacts. So no negative synergy is observed. So no new effect is observed. Just a combination of these two individual impacts. The same, so for the compressive strength, so the results of the compressive strength tell the same story. Those, you can say the same thing. When we use lignin and oil together, the compressive strength decreases, and this decrease is the sum of these two, of the decrease of the two additives when we use them separately and individually. So no interaction, we can see it's no interaction between oil and lignin, and their effects is individual and no synergy between these two additives. So looking ahead, the next steps of this work focus on deepening our understanding of how this additive influence the cementitious materials properties at both the microstructural and concrete scales. At the microstructural level, so we aim to complete our analysis in order to identify the phases formed and better understand their effects on compressive strength and hydration, and to find this link between these two properties. And at the concrete scale, we will extend the study in order to analyze their use in a realistic and in a real construction conditions, and then evaluate their effects on the fresh properties, the compressive strength of the concrete, the durability of the concrete, and also the thermal conductivity, in order to see their behavior and the real construction conditions. And thank you.
Good morning, everyone. I will finish this presentation by making a short overview of how we can use lignin and waste cooking oil in asphalt pavement. So, first of all, in laboratory, as Hamza present for the concrete materials, we do the same thing for asphalt materials. So, asphalt manufactured at high temperature. And normally, we heat the bitumen and we heat the aggregate and we mix them at temperature above 100 degree. So in order to obtain the binder, when I say binder, it means a mix of bitumen, a blend of bitumen, lignin, and cooking oils. We first produce the binder by heating the bitumen, the lignin, and the cooking oil at 130 degree in order to obtain a homogeneous blend. And after producing this blend, we need to characterize the blend for petroleum bitumen. We have two standard laboratory tests. There are the basic experiment we shall do on bitumen when we want to choose a bitumen for road application, because the type of bitumen we shall use depend on the climate and many parameters. So we first performing the two experiments. The first one is called A softening temperature experiment. It is picture in the middle. I want to go deeper in the test. It is a standardized test. You can have more information by taking a look on the EN 1427 standard. It's allowed to determine the temperature at which the bitumen soften. And the second one is a penetration test. It's also standardized. You have here the information regarding this standard. This test is performed at 25 degree, and the principle is to to allow a needle submit to a mass of 100 grams to penetrate in the bitumen. And if the bitumen is harder, the needle don't penetrate deeply. And if the bitumen is softer, very softer, the needle will penetrate deeply in the bitumen. And those two tests allow to classify the bitumen. And for example, for road application, I color here in a red rectangle. For road application, the type of bitumen we use. When I write here bitumen 2030, it means that the needle penetration is between 20 and 30, and the softening temperature is between 55 and 60, 63. And those two tests allow to classify bitumen and to choose the right bitumen to build a road in the right climate. So we perform those two tests on the blend we produce by mixing bitumen, lignin, and cooking oils. And here I show you some results. It's not all the results. I select uh, the good one. We tested several combination. For example, when I write here B30L3G, it means that bitumen with 30% of lignin and 3% of B fat. Uh, and in the right side of the slide, you can see here the evolution of in blue one, it is the needle penetration test done performed at 25 degree, and the green one represents the softening temperature. In general, we have this type of evolution. When the needle penetration increase, the softening temperature decrease. And on the left, we have a classical bitumen. It's the pure bitumen coming from Aerobitume company who provide this bitumen, and the other ones are the combination of lignin, bitumen lignin, and several uh, two type of oil here. In reality, we tested a lot of free type of cooking oils, and more than those combination of bitumen, lignin, and cooking oils. And I just select those one because they fall within a range of bitumen we normally use for road construction. In the rectangle here, you can see it's some example of bitumen. Those one in this part are too hard to use for road construction, and those one are also too soft. So in general, we use the bitumen we call 5070 or 3550. That is why I select only the blend we produce that fall within this range.